implemented this methodology in the area of semi-solid and solid-state lithium-ion batteries and the related anode and cathode materials. We started after myself and Michael Schmid had worked at Imerys Graphite and Carbon in Ticino, myself in product development of active materials for lithium-ion batteries, and Michael Schmidt on the purchasing side, so bringing in some commercial insights, and then very importantly, Andreas Schweitzer, who has a very deep IT knowledge, in particular how to structure databases with R&D related information. So we are a distributed team in Switzerland. I'm full-time and the domain experts support me. And in the meantime, we have also signed a collaboration agreement with Dr. Michelle Lynch from the UK, where as a next step, we plan to expand this methodology and implement it together with her in fuel cells and electrolyzers as well. Another planned expansion is towards battery engineering, while today the focus is on more on the materials and cell side. If we look in a general way of what we try to do and who we try to support, at the core is the product development process and product life cycle that has of course existed for a very long time in high technology environments and companies, but continuously is of course or arguably the key process to maintain superior competitiveness for a company. And so what we would like to support technical decision making in the early stage, conceptual design, the invention of novel products with high added value. And here it is important to understand the state of the art also in the patent literature to make sure one doesn't come up with and spends a lot of time on things that have already been done, instead doing something new. Then usually one gets to the detailed design where application performance, safety and cost requirements have to be carefully matched to a specific first application where the product will be launched. So in this context, one then has to go into the details and understand, try to understand the technical options, decisions that have been made already, and what has not yet been explored. And understanding these decisions also then provides for the input for cost calculations. Then the market introduction phase is very important, and especially in the battery sector, the amounts of investments that are made to develop products are really increasing dramatically. And so I would argue here one has to carefully balance the scope of a project and the goal and the resources that are made available. So here too, understanding the technical environment can allow for providing the right amount of resources to make sure that products are launched on time, or at least in a way that is not late in comparison to other companies. That is very important. Finally, during the operation phase, especially in the battery field, a new battery technology has often a very, very long lifetime, as long as it is adapted for as many additional applications as possible, where one has to understand the extent to which adaptation is necessary, which can include performance, safety, and costs. So what's new? In our opinion, machine learning is something that also will support and to some extent evolve the way technical decisions are made. So that's a new factor that should be introduced in a as efficient a way as possible to try to move this field forward, especially in the context of climate change. And so we see three domains. The first domain is experimental design and analysis. So that's processing of proprietary information, or at least in-house information that has been generated. And so almost every research group probably has to get into this domain themselves and see how to use the machine learning, and that absorbs already a lot of resources. However, in the area of technical literature, which includes academic literature, but in particular the patent literature, machine learning can also help with getting a handle on this enormous amount of information and then condensing it in a way that allows for informed decision making without spending too much time, which should be spent on experiments and invention making. But we should not forget the weakly structured information, especially the panel discussions, because this information often relates to judgments, for example, trade-offs between costs, performance, safety, etc. And so this should also be incorporated, but we think as a service we can provide this processing of publicly available technical information with the help of machine learning, and then providing it in a time-saving way to improve, in particular, product development decisions, but also decisions related to it in the context usually of product launches. But also we have academic customers who of course are interested in developing technologies that could be, for example, spun out into a startup, and for that reason would like to be informed, but not without spending too much time on the industrial state of the art. So to point out again the key issue that in the academic world there is really a very good system in place with the peer review process, I think, that allows for reading the most important breakthroughs to a varying degree of generality, like the most general journals that cover all of science, and then you can get to more and more specific journals, but in each case there is a editorial and peer review process. The patent literature, which also is published in many languages, it is not set up that way, so it's a huge amount of information, and one should try to identify those breakthroughs that are relevant, commercially relevant, I would say, in the sense of being relevant to product development in our case. So what we try to do is an assessment which is related to a judgment of when a new patent family comes out. It has not yet been granted, it's an application, what the future commercial relevance could be. And this, of course, involves knowledge of the market, of the players. Perhaps to some extent it is subjective, but if one tries to do a good job, one can get to about 10 to 100 commercially relevant published patent families, which we identify every 3 weeks in 10 lithium-ion battery materials categories, fuel cells, and supercapacitors. So this is at the same time a way of training a machine learning model, which then takes for now as the input title, abstract, applicants, but also the IPC classification assigned by the patent offices, and then generates a score based on how it was trained. So this is a way of kind of condensing the more than 100,000 battery patent documents published every year into a quantity that can then be further processed by a human and analyzed and visualized. Of course, this can be further developed, which is also our plan once we have this training data that we can further develop, but this is then of course a bit the proprietary part of our methodology. But let's say the visible part, I would argue, is also very important in the sense that it is to some extent maybe something new to have this kind of visualized graphs that then our users and customers rely on, partially at least, to make technical decisions. And so this is an example. The solid and semi-solid electrolytes, the key ones being evaluated from the based on the analysis of the patent literature, and also following what's being talked about at conferences, news releases. So at a very prominent one is of course sulfides, but the field it's very interesting how this field is wide open while enormous investments are being made to put this already often into EVs, so into a very large volume application. There are goals, for example, by Toyota to put sulfide electrolytes into commercial EVs, while other companies focus on entirely these different material classes. So it's very interesting, but also risky for the companies, and it is not yet clear which ones will gain substantial traction. So with sulfides, the key advantage is lithium-ion conductivity as a class. So of course that makes sense. It's very important for power performance in particular. But then the risk factor is also potentially very severe, that upon contact of sulfides with water, you can have hydrogen sulfide gas emissions, which is a highly toxic gas. And so because that is the case, you don't see these cells yet, let's say in mobile phones, because I would argue that it is very important for these kinds of cells to have a very high recycling rate, to have a controlled environment, so that there is no contact with water. So Toyota is a key player here, but this kind of context then explains why oxides and phosphates as a material class are also studied fervently, for example, by Volkswagen together with QuantumScape, because there is an advantage in terms of not having this risk of hydrogen sulfide gas emissions. But the lithium-ion conductivity as a class in general is lower than for sulfide. So that creates also a substantial risk of whether power will be enough, energy density and longevity will be enough in EVs. Then it is important to point out also that there are EVs on the road already, especially buses also based on solid polymer electrolytes. Excuse me, developed by Blue Solutions in France, adopted by Daimler. As a class, polymers have even lower lithium-ion conductivity. So these e-buses, for example, are usually operated at 80 degrees. So again, it is very interesting to see whether or not in the end one will operate the batteries at room temperature, which of course, has been the case or is the case now in most EVs. But there is this effort and let's say the compromise that has been made to operate them until now at least at elevated temperature. So it's another development and commercialization track. Then there are halide electrolytes that are not talked about so much, but these are very well balanced and pursued by Panasonic. Often there some raw materials have been used that perhaps are scarce, but very recently Samsung has made a very interesting, there has been a patent published by Samsung that is based only based on lithium halides, chloride, bromide, and nitrogen. Then there are the thin film solid state devices that I will not talk about today, but these have been on the market for many years already in the Internet of Things, for Internet of Things applications, but these are difficult to upscale because of vacuum processes. Then there are the eutectic salts that are promising in combination with other electrolytes listed here. I will talk about this further later. And then there is also the approach to use still some liquid electrolytes together with ion conducting salts in an inert support matrix. So here it's kind of it's not fully solid, but let's say the target is usually to harvest most of the benefits of solid components combined with some liquid components that usually provide high lithium-ion conductivity. So this was an overview. And then another part of let's say, the methodology we wish to promote is that one looks at the desired outcome at cell level and then tries to connect these targets to material requirements and then identify material components, because especially in East Asia, where a large part of the lithium-ion battery industry is located, there is often a lot of pragmatism around combining different materials classes. And so here we attempted to visualize and rationalize why the combination of oxides or phosphates, ceramics with polymers can make sense, because if one takes the desired outcome performance aspects of fast charge discharge, high cycling stability, high energy density, and the prevention of short circuits, these can be connected, for example, to sufficient ion conductivity in terms of fast charge discharge, which then certainly is an advantage of oxides or phosphates as compared to polymers. On the other hand, making a thin electrolyte layer is very important too for several reasons: energy density, fast charge, discharge. And this then is quite well possible by combining polymers with oxides. It's quite similar to what is often done in the coatings industry of using inorganic fillers with polymers that have a binding function to have thin films. So this is then a reason or an area with synergies. And then polymers usually have lower density than the oxide. So you overall have a lower density, which helps for energy density. And finally, polymer can often fill defects, holes, cracks in between inorganic particles. So this is kind of, after identifying the key materials classes, these kinds of visualizations try to inspire. We try to inspire innovation and inventions with these kinds of visualizations, because you then, of course, can still or have to adjust many materials characteristics, and the invention lies in the experiment in batteries in general, because it's still hard to predict results. I have also included additional diagrams. I would certainly be happy to share the presentation. So this is the combination of inorganic materials with lithium salts here in short, especially if the eutectic lithium salts melt at a fairly low temperature. One can basically do a melt infiltration of a inorganic thin film that often contains some pores or some cracks. So this is an interesting approach, combining lithium salts with inorganic electrolytes. And then also this was done by Toyota and Panasonic, combining sulfides with halides, which also possibly the halides might fill defects in the sulfide layer and help with processing based on a pressing or molding approach. So if we now look at the market entry projections, it's very important to point out that Blue Solutions has operated rental EVs since 2012 that are solid state lithium metal batteries, usually operated at around 80 degrees Celsius. This technology is being adopted by Daimler for e-buses. The key partner here is Hydro-Quebec from Canada. Then Dongfeng Motor in China works with Ganfeng Lithium. Based on the patent literature, this can be projected as probably an oxide phosphate polymer hybrid system discussed in the prior slides. And here it seems, the target was Q1 this year for the launch of solid state EVs. It seems the first caps have been put into operation. And I should point out that actually the market entry challenge in a way is perhaps not that high, in the sense that we can expect these technologies to come in at the high end actually, or maybe in caps applications in specific niches, but especially at the high end. So in small quantities at the high end, based on first of all a safety advantage, then to some extent also a range advantage, and then the EV makers can tune with the pricing how much volume has to be produced, and then gradually increase the volume while lowering the costs And so that would be my expectation, so that there is probably a gradual increase of solid state or semi-solid EVs at the high end that then goes further and further towards high volumes. So then also NIO is working, it seems, on a similar system, and then we have Toyota, which has for many years worked on sulfide electrolytes, but it seems it's still not clear whether the decision to launch these EVs has been made, because it was promised that a demo would be made during the Olympics, and that was not made. Instead, there is a YouTube video of a solid state EV on Japanese roads, but it seems that Toyota did not yet decide to make a high-profile introduction and face all the questions around the toxicity and risks in that regard of sulfides. Then we have VinFast that is working on with Prologium on bipolar cell architectures, and then prominently Volkswagen working on oxides, then a whole range of major EV producers, Ford, Nissan, Renault, Mitsubishi Motors, BMW, Hyundai, with Kia focusing on sulfides. And finally, Ilika from the UK is developing oxide electrolytes and works with Jaguar, Land Rover, Honda. Now, the story gets even more complex, but it's, I think it cannot be avoided, because the cell design might also change substantially when working with solid electrolytes. Bipolar cells are very attractive because they could allow for improved energy density at the pack level, because one can make cells based on many electrode pairs separated by polar layers that then have already quite high voltages from 40 to maybe 200 volts. And that could facilitate a lot of things at the pack level. But the production of these kinds of cells is very challenging, in particular avoiding formation of short circuits and the growth of lithium dendrites between these many layers, which all should work and not fail, as there is a serial connection. So it leads to this, let's say, what I would characterize as a roadmap towards increased pack energy density in terms of the technical decisions that have been made in this context, that are twofold in terms of the key decisions, whether to focus on lithium metal anodes or silicon carbon containing anodes, and whether or not to target bipolar architectures or conventional ones. And so here you can see that if a cell is not bipolar, basically a typical target is about 1000 watt-hours per liter by QuantumScape. Prologium, which works with silicon oxide carbon anodes, has more of a gradual set of targets, because they gradually increased silicon. And in that sense, first, they are below QuantumScape, although they already produce cells, unlike QuantumScape, and sell them for specialty applications. But then, because of the bipolar cell design, there is a 25% energy density boost, let's say, at the pack level. And so that is then principally very attractive if it can be put into production at with sufficient quality and at acceptable costs. And so, yeah, one can understand why different decisions are being made, because yeah, the risks are then concentrated at different in different places. So because the bipolar cells, there is of course the risk if it doesn't work, then prolothium also does offer non-bipolar cells, then the energy density is a bit lower, but there is this opportunity to do it gradually, while with lithium metal that is basically 100% lithium metal. And then of course there's the question, is it possible to combine lithium metal anodes with bipolar cell architectures? That is a very big challenge because of the risk of lithium dendrite formation that can form short circuits. But in the sulfide area, there has already been this patent by Nissan Renault that is involves lithium metal and sulfide electrolytes, and it's at proof of concept level. So looking one more time at the, or looking at the cell, how what happens when one uses lithium metal. Principally, one has to deal with this change of thickness during cycling that implies that one has to be very careful at the edges of the cell, that one does not have undesired deformation at the edges that then in the worst case leads to short circuits. And so that is a key challenge with lithium metal negative electrodes, while if one has silicon in there, principally there is also volume change, but it is not necessarily as much connected to change of thickness. I should mention also that there are efforts to deposit the lithium metal inside columns, let's say, or inside a matrix to avoid this change of thickness. So when we look at the technical decision tree one more time with respect to negative electrode materials, I discussed already several points, but it's important to mention there is also LTO, a lower energy material used a lot by Toshiba. I will get back to this. And then there are these three branches: silicon-based electrodes, like based on silicon-based materials, silicon oxide, and graphite. So if we look at the silicon ones and what Toyota is patenting, it's interesting to see how they produce porous silicon structures that might have quite a high surface area that with liquid electrolytes would cause probably too many side reactions. But with a sulfide electrolyte, it seems there are not too many interface reactions, and the volume expansion of the silicon can be accommodated by having this void volume, although it should be filled with electrolyte, but it's a way of distributing the volume change and avoiding crack formation. Then there is a very interesting result recently by LG Energy Solution and Professor Shirley Meng's group now at the University of Chicago Argonne National Labs, where they showed that even one can use silicon microparticles without carbon, and if one uses sulfide electrolytes, they found favorable cycling results, which in a liquid electrolyte system that would be pretty much impossible to it's up to now at least to achieve stable cycling. So it is really a big question whether like this could commoditize the anode materials industry, if that really works, because microscale silicon is available and has low costs. So in the most optimistic case, that could happen, but it could also be that still silicon with nanostructure that allows for the avoidance of crack formation will be used. So here I'd like to introduce another cell design that is pursued by SWOLT and ATL, another very pragmatic approach, because it is a semi-solid cell design where in the middle between the electrodes we still have liquid electrolytes and separators. If one doesn't look at it in detail, one would say, okay, the goal has not been achieved to remove the liquids, but the liquids are prevented from being in contact with the positive and negative active material particles. And that is very important, because that's where most parasitic processes occur and where thermal runaway processes and safety related processes tend to occur. And so these companies, when they coat the electrodes, or one could also produce them in a dry way, they use solid electrolytes to be in contact with the active material, and then they construct the cells in the same way as is done now. And so from a chemical point of view and from an interface point of view, this I think can make a big difference, and is a way of combining the positive aspects of the solid electrolytes, avoidance of parasitic reactions, and of liquid electrolytes, which remains favorable lithium-ion conductivity, especially between the electrodes where there is a relatively large distance. And so here a lot of companies have started to deposit silane gas on carbon, and other companies have been active in the field already for many years. And this way, one can, for example, produce silicon nanowires, or one can fill porous carbons with nanoscale silicon. And this way, one then has already the silicon distributed on the carbon prior to the electrode formation. So if one then forms the electrode, it has traditionally been very important to distribute the silicon well. But in this case, the silicon is already connected to the carbon and distributed. So here the important question is, especially in the context of Tesla pursuing dry electrode fabrication processes, which exhibit lower costs, if this works, whether these materials will be used in this context, in a semi-solid cell environment. Then going to the positive electrode material side, here I would point out that often to avoid too many risks at the same time, NMC materials are used in solid state or semi-solid cells, but there is the attraction of using manganese-rich spinels, which because manganese is more abundantly available or has a lower cost than nickel and cobalt, and has not been used that much. I would say manganese-containing spinels have not been used that much with liquid electrolytes because of manganese leaching and the high voltage. But here there is a very interesting cell chemistry developed by Toshiba, where they used manganese-rich spinel together with LATP solid electrolyte and an LTO-based electrode that usually allows for fast charging, and that's what they already promote with their existing cells that are often based on LTO, and also a high cycling stability. And so this system I have seen only in the patent literature, no news releases by Toshiba so far, but I wouldn't be surprised if it would be launched fairly soon into the market. So finally, myself, although I'm a chemist with a background on the material side, we have some customers in the automotive area that would like to or rely on our information to make projections on how future cell and pack design looks like once these new cell technologies are upscaled, and so I'd like to make some, or I thought I would include some projections from a materials point of view. So, for example, for cells with oxide or or phosphate polymer electrolytes with silicon carbon negative electrodes, one can really expect that even severe deformation or nail penetration will not cause a fire or explosion, and so presumably that leads to a much reduced need for mechanically rigid packaging and compartmentalization. So presumably that could lead to cost reductions and volume mass reduction at the pack design level, at least. Yeah. And so on the other hand, with lithium metal electrodes, here there is the aspect that depending on the surface area upon cycling, upon contact with water, this can react violently, and so presumably these pack designs might be closer to what we know from today, but it's a bit hard to project. On the other hand, sulfide electrolytes, there it's just they are not necessarily. I wouldn't expect that fires can easily start, but if there is contact with water, there is really this big risk of toxic hydrogen sulfide gas emissions, so it has to be considered during the whole operation and also during recycling. So I would be optimistic in terms of large-scale stationary storage, because that is a very controlled environment. But for EVs, it will have to be seen to which extent it will be accepted by regulators and the end users. Then thermal management, it is really quite feasible that the maximal temperature will rise to 120 to 140 degrees, the maximal operating temperature, which presumably will allow for energy density and cost advantages at the pack level. Finally, the form factor, it's almost always a stacked design, but otherwise there is a lot of flexibility and so-called cell is pack designs without modules are being pursued, and also cell to chassis designs where one does not really have a pack, but very much integrated a battery into the chassis. With lithium metal negative electrodes, there is the question if pressure will be needed, and that appears probable, about 3 atmospheres, and that presumably would require more rigid shells. Many thanks for your attention, and I'd be very happy to answer any questions and take any comments. Many thanks.
Thank you, Mr. Ullmann, for this very interesting presentation. So I propose that those who have a question just quickly raise their hand and unmute. I can tell who's having a question here. So let me jump in with a question from my side, Mr. Ullmann. I saw that your sources are actually not only the traditional sources, which would be the patent databases like ePatisNet and so on, but you mentioned also news and especially podium talks and so on. And I was wondering, how do you actually integrate this knowledge into your machine learning database? Is this some manual work you do, or you have some web crawler who's looking for some keywords and then tries to extract data? Just out of curiosity, how you organize this?
Yes, it's a very good question. It is indirect at this time, in the sense that when we create a list every 3 weeks, where we actually then also, like, we create a ranked list, and the first 3 patents we discuss briefly for our users and customers. And so there, let's say the applicant is very important, let's say LG or Toyota, and but also others. And let's say, so if I go to conferences, I watch the news, that flows into the judgment. So in a way, it's a low technology, but it illustrates how we try to keep the judgment in the hands of the human, and the algorithm should try to condense the information mainly. And so in that sense, it flows into the ranking because it's future commercial relevant. So on purpose, it is something that you could say, okay, how can you say that? It's not easy. It's looking into the future. So by nature, there could be errors, but that we try to keep at least in the hands of, well, at this time myself or Michel Lynch, somebody who has experience in the industry and goes to conferences, and I would argue that is very hard actually to crawl, because you would have to send a robot to a conference to watch a discussion panel. Of course, news you can read, but the panel discussions are very, very important, I would say, by key companies. And that is what one can see at the conference. And there one can say, another example is we learn about the startup at the conference. We will rank it very, very high in our ranking, and the algorithm will, let's say, it puts it into the first 200 results. But myself, I put it then at the very top, and that then should be picked up later on by the algorithm that company is important. So in a way, it is on purpose keeping the human in the loop, and for that reason, up to now, we could also do this with the help of Amazon Web Services, where we are hosted, which provides very valuable machine learning frameworks and tools, of course. So it is certainly important, the machine learning, but it is very much supervised. is it understandable or does it make sense?
Yes.
Oh,
I
okay,
think the
thank you.
quality of the data is, if this approach, naturally higher than if you just had automated robots crawling. There's another question from Christian Vögtli, who says that often energy densities in watt-hours per liters are mentioned. And he was more curious about watt-hours per kilogram, which could be expected. Example for prologium, which you showed, but which is actually also not mentioned on the homepage. Basically, I think typically engineers like more the watt-hours per kilogram in a way.
Yes. Yes.
Does it scale the same way as
that's
standard? Or, yeah.
Yes,
Sorry.
yes. So let's say you have 1000 watt-hours per liter. That would usually be about 400 watt-hours per kilo. So because basically, if you go back to the presentation, and then I have in some cases they have a target of about 600 watt-hours per liter, and that is even a bit below what is now available with liquid electrolytes. So to some extent, they are coming in at the cell level prologium below what current cells provide, but they have the bipolar architecture. So at the pack level, then they have a 25% advantage if that works, and so that's how they might get back from let's say 600 watt-hours per liter, and that would be 250 watt-hours per kilo maybe, and that would be a bit below, maybe if we say we might be close to 300 watt-hours per kilo with liquid cells. That would be a bit below, but then they get there with the bipolar, but the safety remains the key point still. Not yet necessarily the energy density, they are working on it, but for now the safety is the key factor, especially in the specialty applications, let's say mining underground or something like this, that there is a safety advantage. And then, then I said 1000 is about 400 watt-hours per kilo. And then there are some very high energy density systems with close to 1300 watt-hours per liter. That will be getting close to 500 watt-hours per kilo, which is very, very challenging, and still in, let's say, in satellites, maybe deployed in satellites, or usually with liquid electrolyte. The key company there is Amprius, and they work with liquid electrolytes for now. Yeah. Is it fine, the response?
Yeah. I saw Amprius just recently said that they commercially made available 450 watt-hour per kilogram. That's I think the upper limit what is at the moment available.
Yes.
Christian, you're
yeah, that's good. I'm fine. Yeah, thank you for this answer. Yeah,
good.
Thank you.
Okay, any other questions from the public? Either in the chat or just leave your hand. If this is not the case, I would like to thank you very much, Mr. Ullmann, for the presentation, which I found very interesting. It confirms a bit my hope and also my belief that battery technology development is still not finished. There's a lot to come, and I think this is an exciting time, actually. And just to finish now within the time frame, let me allow you to quickly show you two more slides. I just want to show that within 1 month, on April 5th, we will have Twice Energy AG, which will present their business model. This is then again more on the application side. This is a cycle they actually promote second life energy storage system, so closing the circular economy approach to actually use the resources to its maximum and at highest intensity. So we're looking forward for this presentation from Twice Energy AG. And just a last reminder here, the annual program, we have now fixed the date, or the date has been fixed for the Industry Day at the Swiss Battery Days. It will happen on the 31st. The whole Swiss Battery Days will be from 29th to 31st. And again, the date for the annual conference has been fixed to November the 1st. At this moment, I'd also like to remember you that you actually will find on our webpage under events, not only our annual calendar, but some partner events here, especially the international events. So that's, if you don't remember where is which conference, this is a quick overview which you can go and have. Finally, I'd like to thank everybody, especially Mr. Ullmann for the presentation, for all the participants. We had a very good participation with 29 people, and I really appreciate the format. And I find it very interesting that we switched from the academic institution now more to the industry side for the presentation. And I think this gives a very good opportunity to get to know each other better, but also to get a good overview on who's doing what on the Swiss battery landscape, which is basically one of the goals of iBAT. So with these words, I'd like to close and wish you a very good rest of the day or an evening. Thank you very much and see you in 1 month again. Bye-bye.
Bye. Danke. Tschüss. Thanks a lot. Bye.